Imagine a future where humanity thrives on Mars. But how will they talk to us? How will they stay connected with each other across the vast Martian landscape? The answer lies in an intricate web of cutting-edge technologies designed to bridge the immense cosmic distance and overcome the unique challenges of interplanetary communication. For humanity to truly establish a foothold on the red planet, robust and reliable communication is not just a convenience. It's a fundamental necessity. Astronauts will need to communicate with mission control on Earth, share scientific data, receive critical updates, and even connect with loved ones. On Mars itself, surface teams will require seamless communication for exploration, construction, and daily operations. This isn't just about sending a message, it's about building a digital lifeline across millions of miles. Our vision for Martian communication rests on three primary technological pillars: a dedicated Martian satellite network, the venerable Deep Space Network, DSN, and sophisticated relay operations utilizing orbiting spacecraft. Each plays a distinct, vital role in weaving the fabric of interplanetary communication. Just as Earth relies on a vast constellation of satellites for global connectivity, Mars will need its own orbital infrastructure. A network of satellites circling the red planet could provide planet-wide internet coverage, effectively extending Earth's digital reach to another world. This Marslink system would function much like terrestrial satellite internet providers, but on an interplanetary scale. Consider a proposed system of dozens, or even hundreds, of low-orbit satellites. These would form a mesh network, ensuring continuous coverage for surface operations, rovers, and future human habitats. Such a system offers significant advantages. It's more economical than deploying numerous ground stations, and it provides ubiquitous access across diverse Martian terrains. This network would facilitate local communication between Martian outposts, enable high-bandwidth data transfer from scientific instruments, and serve as a crucial link to Earth. The Deep Space Network, DSN, is NASA's international array of giant radio antennas that supports interplanetary spacecraft missions. With sites strategically located in California, Goldstone, Spain, Madrid, and Australia, Canberra, the DSN provides continuous 24/7 coverage as Earth rotates. These massive dishes, some over 70 meters in diameter, are the primary conduit for communicating with probes and rovers far beyond Earth's orbit, including all current missions on Mars. The DSN is the backbone of our current Martian communication. It receives faint signals from distant spacecraft and transmits commands with incredible precision. For future human missions, the DSN will remain indispensable, serving as the primary gateway for high-volume data exchange, critical command uplinks, and emergency communications between Earth and Mars. Its unparalleled sensitivity and global reach make it an irreplaceable asset in our interplanetary endeavors. Sending signals directly from the Martian surface to Earth requires significant power, which is a precious commodity for rovers and landers. This is where relay operations become invaluable. Instead of direct communication, surface assets transmit their data to orbiting spacecraft around Mars. These orbiters, equipped with more powerful transmitters and larger antennas, then relay the data back to the DSN on Earth. NASA's Mars Relay Network currently comprises several orbiters, including the Mars Reconnaissance Orbiter, MRO, Mars Odyssey, and MAVEN. These spacecraft act as high-altitude data couriers, collecting information from rovers like Perseverance and Curiosity, and then beaming it home. This method conserves power for surface equipment, allows for higher data rates, and provides more frequent communication windows than direct-to-Earth links. For human missions, An expanded and more robust relay network will be essential to handle the vastly increased data volume from crew activities, scientific experiments, and habitat monitoring. While the technological solutions are promising, communicating across interplanetary distances presents formidable challenges that demand innovative solutions. These aren't mere inconveniences. They are fundamental physics and orbital mechanics at play. The most significant hurdle is latency, or the one-way light time, OWLT. The distance between Earth and Mars constantly varies, ranging from approximately 54.6 million kilometers at closest approach to over 400 million kilometers at farthest. This means a radio signal traveling at the speed of light can take anywhere from 3 minutes to over 22 minutes to travel one way. This inherent delay rules out real-time conversations, video calls, or interactive control of Martian equipment from Earth. Imagine trying to have a conversation where each response takes 6 to 44 minutes to arrive. Astronauts will need to be highly autonomous, and mission control will operate on a store and forward basis, sending instructions and receiving data packets with significant time lags. This psychological and operational challenge will profoundly impact mission planning and crew well-being. Approximately every 26 months, Earth and Mars find themselves on opposite sides of the Sun. During this period, known as solar conjunction, the Sun's intense plasma and radiation interfere with radio signals, making communication unreliable or impossible. This blackout can last for several weeks. During solar conjunction, missions must either cease communication entirely or rely on highly attenuated, error-prone signals. This necessitates careful pre-planning. Critical commands are sent before conjunction, and Martian assets are programmed to operate autonomously, collecting data that will be stored on board until communication is re-established. For human missions, this period will require heightened self-sufficiency and robust onboard systems. Despite advancements, the bandwidth available for long-distance space communications remains limited compared to terrestrial networks. Sending vast amounts of high-resolution imagery, video, and scientific data across millions of miles requires immense power and sophisticated encoding. Signal strength diminishes rapidly with distance, meaning only a fraction of the data rates we enjoy on Earth are feasible. This limitation necessitates efficient data compression, prioritization of critical information, and careful scheduling of data transfers. Future missions will require significant leaps in bandwidth capabilities to support the data-intensive needs of human exploration, including medical telemetry, environmental monitoring, and high-definition scientific observations. The harsh Martian environment also poses communication challenges. Solar and cosmic radiation can degrade electronic components and introduce noise into signals. While less impactful than latency or conjunction, severe Martian dust storms can also attenuate radio signals, particularly for surface-to-orbiter links, adding another layer of complexity to communication planning. To mitigate these formidable challenges, space agencies and private companies are developing and considering several innovative strategies, pushing the boundaries of communication technology. Given the significant communication delays, systems on Mars, from rovers to habitats to the astronauts themselves, will need unprecedented levels of autonomy. This means equipping them with advanced artificial intelligence, sophisticated robotics, and robust decision-making capabilities. Rovers already demonstrate this, navigating complex terrains and making scientific observations without constant human intervention. For human missions, autonomy will extend to life support systems, power management, and even medical diagnostics. Astronauts will be trained to handle a wide range of contingencies independently, relying on Earth for high-level guidance rather than real-time control. This shift towards self-reliance is fundamental to safe and effective long-duration Martian missions. Reliable communication demands redundancy. This means having multiple communication paths, diverse technologies, and backup systems. For instance, a Martian outpost might have several antennas capable of communicating with different orbiters, which in turn can relay data to Earth via multiple DSN stations. Implementing diverse communication protocols and hardware ensures that if one system fails, others can take over. This layered approach minimizes the risk of communication blackouts and enhances the overall resilience of the Martian network, crucial for the safety and success of human endeavors. To reduce the constant need to communicate with Earth for every piece of information, future Martian settlements will likely establish local servers and data caches. Imagine a Martian intranet, where frequently accessed data, maps, operational procedures, scientific databases, entertainment is stored locally. This would significantly reduce latency for internal operations, allowing astronauts to access information instantly without waiting for a signal to travel millions of miles. It would also free up valuable bandwidth for critical Earth-Mars communications, making daily life and work on Mars far more efficient and less dependent on the cosmic umbilical cord. One of the most promising advancements for future interplanetary communication is optical communication, or laser communications. Instead of radio waves, these systems use focused laser beams to transmit data. The primary advantage is vastly increased bandwidth. Laser systems can transmit data at rates orders of magnitude higher than traditional radio frequencies. NASA's Deep Space Optical Communications (DSOC) experiment, currently flying aboard the Psyche mission, is testing this technology. While challenges remain, such as precise pointing over vast distances and atmospheric interference, the potential for gigabit per second data rates from Mars is transformative. This could enable real-time, high-definition video streams, massive scientific data dumps, and a much richer connection between Earth and Mars. Looking even further into the future, quantum communication offers intriguing possibilities, though it remains largely theoretical for interplanetary distances. Concepts like quantum entanglement could potentially enable ultra-secure communication channels. While not allowing for faster-than-light information transfer, quantum technologies might offer unprecedented security and novel ways to encode and transmit data, pushing the boundaries of what's possible in cosmic connectivity. This is a nascent field, but one that space enthusiasts eagerly watch. The journey to Mars is not just about reaching another planet. It's about building a sustainable human presence there. And at the heart of that presence lies the ability to communicate. From the foundational deep space network to the visionary Mars satellite constellations and the cutting-edge promise of laser communications, every technological stride brings us closer to a truly connected Martian future. The challenges are immense, but the ingenuity of humanity is greater. As we continue to push the boundaries of space exploration, the development of robust, high bandwidth, and resilient communication systems will be paramount. It will ensure that even as we venture millions of miles away, we remain connected, a single, curious, and communicative species, reaching for the stars. Are you fascinated by the future of space exploration and communication? What technologies do you think will be most crucial for connecting Earth and Mars? Share your thoughts in the comments below. Don't forget to like this video, subscribe to our channel for more deep dives into space science, and hit the notification bell so you don't miss our next cosmic adventure. Let's continue to explore the universe together.